All right, so we're looking at class 64. Our goal is to identify and differentiate parts and types of waves, and we're going to measure some parts of waves. So the first thing we did in class was we watched a couple videos and wrote down some similarities and differences between the different waves we saw. You could check that out if you'd like. Just go on Google Classroom, click on those links in the notes. We're going to skip down for now to part A, mechanical waves. So a wave is a disturbance that carries energy through matter or space. So our first type of wave is a mechanical wave. It requires a medium, so it has to go through something, whether that be water, air, a rope, a spring, just like what we've seen in class. Now, on the other hand, light waves do not need a medium, but we're going to go into those next unit. So to just do some basic definitions, a wave pulse is a single bump or disturbance that travels through a medium. So the first type of wave we have is a transverse wave. And that's a type of wave that vibrates perpendicular to the direction of the wave's motion. So light can be an example of a transverse wave. The ropes that we've shown in class, those are examples of transverse waves. They look kind of like this. It's that classic picture of a sinusoidal wave that you're probably familiar with. Now, longitudinal waves are a little bit harder to picture. So longitudinal wave is one that vibrates parallel to the direction of motion. So sound is an example of a longitudinal wave. That's this image up here. It's kind of like a compression wave where the medium is constantly compressed and decompressed. We'll talk more about that when we get into sound. So back in earth science class, we learned about P waves and S waves. A P wave, that's an example of a longitudinal wave. And an S wave is an example of a transverse wave. So if you look at the pictures, that's kind of obvious, but one way to also look at it is if you look at this little part here that says particle motion right here, it shows you here that as the direction of the wave is going to the right, the particles here in the longitudinal wave oscillate left and right, parallel to the direction of motion. If we look here, the wave is moving to the right, but the particles are oscillating up and down, so that's what makes it a transverse wave. Up and down is perpendicular to left and right. So the amplitude of a wave is the greatest distance from equilibrium. It's always positive. And for any mechanical wave, greater amplitude means greater energy. Now that's different than light waves. Light waves, greater frequency is greater energy. But for any mechanical wave, greater amplitude, greater energy. Now a wavelength is the distance from the crest of one wave to the crest of another, or the trough of one wave to the trough of another. Another way, the way I count waves, is I count from where one wave starts right here to where the wave ends right here. Okay, like one sinusoidal wave, one sine wave. So in the image above, the amplitude is 0.2 meters. Just be careful. A lot of people like to say that it's 0.4 meters, but 0.4 meters is that total size of the wave, not the amplitude. Amplitude is from equilibrium up or from equilibrium down. The wavelength, let's see, for the wave that I sketched before, that's from about 0.3 to 0.7. So the wavelength looks like it's about 0.4 meters. You could also measure from one crest to another. So for example, one of the crests is right here at 0.4. The other crest is at 0.8. So we have 0.4 meters as our wavelength. Looking at some practice multiple choice questions. The first one asks, in the image below, wavelength is represented by, that would be A, that's the distance from one crest to another. And the amplitude is represented by D, that's the distance from equilibrium to either the crest or a trough, in this case a trough, so it's the greatest distance from equilibrium. So this one's a little bit tougher to do. It's a little hard to read the scale, but you can estimate. So this one says the wavelength of the wave is, so there's a few ways to do that. I like to just count off a wave and kind of measure it out. So if I start here and end here, this wave here, that looks like the wave is about 3.8 meters long. We'll say that that's the unit we're measuring in. and the amplitude. Be careful here. A lot of people look at this amplitude, they just look here and they say, oh, that's about 1.8, 1.7. That is not the amplitude, okay? The amplitude is the distance from equilibrium. So if we look here, the amplitude looks like, let's see, the equilibrium position is about 0.8. And it looks like the top of the wave there is at about 1.8. So we would get an amplitude of about 1 meter. Okay, depending on how you measured it, maybe you got like 0.8, 0.9, but it should be in that range. Just make sure you don't say that the amplitude is 1.8 meters. So the next thing we're going to talk about is phase. We asked the class, how are these two waves similar? How are they different? Some of the similarities people pointed out was wavelength. Those look the same. The amplitudes, those look the same. How are they different? Aside from color, one thing that we have to notice here is that these waves kind of look flipped. Okay, if you look, the blue wave and the orange dotted wave are kind of like mirror images of one another. So this brings us to our next idea, this idea of phase. So phase is the point in the wave cycle of a particular particle. So if you think back to your classes, like your math classes, one full wave cycle is 360 degrees or 2 pi. In this class, we're going to use degrees, so we're going to say 360 degrees. So this question here says, which points are in phase? So I think there are actually two correct answers you could put here. You could put the pair of points O and D. Okay, notice how O and D are both at troughs in the wave. Okay, so we could say O and D. I'll put them in like parentheses like that. Or we could say B and E as well. Now, a lot of people like to say A and C, but A and C are not at the same point in the wave. If you think about it, A is kind of on like the uphill, and C is kind of on like a downhill, so that's not the same point in a wave. Now, which points are 180 degrees out of phase, so that to be half a wave cycle off? There's actually, I think, 4 answers here. Okay, the first one we see are O and B. One's at a crest, one's at a trough. So O and B are 180 degrees or half a wave apart. The next two we see are A and C. They're half a wave apart. One hump of a wave is half of a wave. So A and C. Then we have B and D. Notice how B is at a crest, D is at a trough. And the last one is D and E. D's at a trough, E's at a crest, so we have D and E. Now which two waves are 90 degrees out of phase with point A? So 90 degrees out of phase is a quarter of a wave cycle. So the 2 points a quarter of a wave away from A are points O and point B. The exit ticket from class, let's see, a student generates water waves in a pool. In order to increase the energy carried by the waves, the student should generate waves with. Now remember, this is a mechanical wave, so the answer is going to be greater amplitude. If we were talking about light, it would be higher frequency. Which points on the wave diagram below are 90 degrees out of phase? So we could choose A and B, or we could choose D and E. Well, notice only D and E is a choice. Okay, because those are the two that are a quarter wave cycle away. A, B is not a choice, but if it were there, it could be an answer as well. Now we're comparing A and B, waves A and B. A is the shorter dotted line, B is the taller one solid line. So compared to A, wave B has, so if we just think right away, wave B is definitely has more amplitude. So we can eliminate choices 3 and choices 4. Now we think to ourselves, okay, so it has twice the amplitude, that sounds all right. Does it have twice the wavelength as A, or does it have half the wavelength as A? Well, if we think about it here, it looks like B has a much tighter wavelength, okay, much shorter wavelength. Okay, it's narrower, it's more compressed looking left to right. So I think B is going to have half the wavelength. So it looks like it's going to be choice 2. B has twice the amplitude and half the wavelength. Don't forget to hit the like button, and if you found this helpful and want more videos, don't forget to subscribe to the channel.